Part 1. What a computer actually is. Before we begin, here's an uncomfortable question. You can write a for loop, define a class, maybe even reason about big O notation. But if someone asked you, what physically happens in your computer in the instant after you type x equals 5 and hit run? Could you answer without saying the word computer as if it were magic? Most programmers can't. Not because they're bad programmers, but because almost every book, course, and bootcamp starts in the middle of the story. You're handed a language and told this means that, and you believe it the way a child believes money has value because everyone agrees it does. It works until the day it doesn't, and then you're stuck because you never understood the thing underneath the agreement. This book starts underneath. Part 1 is the foundation everything else sits on. What a computer is at the level of physics and logic before a single line of any programming language exists. By the end, you won't think of a computer as a black box that runs code. You'll think of it as a very large, very fast, very stupid machine that does exactly one thing, and you'll understand why that one thing is enough to build everything else in this book on top of.
The problem of information. Before we talk about computers, we have to talk about information itself, because a computer is, at its core, a machine for storing and moving information. What is information, really? Strip away the philosophy, and information is the ability to distinguish between possibilities. If something can only ever be one way, it carries zero information, there's nothing to learn from it. If it can be one of two ways and you find out which, you've gained the smallest possible non-zero amount of information. That smallest unit, a choice between exactly two possibilities, is called a bit. Now here's the first why that most courses skip. Why do computers use binary base 2 instead of, say, decimal base 10, which is what humans actually use? The honest answer isn't mathematical elegance. It's physical reliability. Imagine trying to build a tiny electronic component that can reliably sit at any of 10 distinct voltage levels, say 0V, 1V, 2V, all the way to 9V, and have a sensor downstream that can tell them apart every time, billions of times per second, even as the component heats up, ages, and sits next to a million other components doing the same thing. The voltage levels would constantly bleed into each other. It's a nightmare of noise and error. Now imagine instead you only need to distinguish, is the voltage closer to zero or closer to maximum? A simple high-low threshold. That's vastly easier to get right, even at extreme speed and extreme miniaturization. Binary 1 not because 2 is a beautiful number, but because on V's off is the most physically robust distinction we know how to engineer at scale. Every other choice in computing, bytes, words, hexadecimal, is a human convenience layered on top of this physical necessity.
From voltage to switches, the transistor. So we need something that can reliably be in one of two states and switch between them billions of times per second, using almost no space and almost no power. That something is the transistor. At its simplest, a transistor is a voltage-controlled switch. It has three connections, a gate, a source, and a drain. Apply enough voltage to the gate and current flows freely between source and drain, the switch is closed on. Remove that voltage and the current stops. The switch is open, off. That's it. That's the entire physical basis of every computer ever built. A modern CPU contains billions of these switches, each one individually doing nothing more sophisticated than a light switch on your wall. Here is the first genuinely mind-bending idea, and it's worth sitting with. A transistor has no idea it's part of a computer. It doesn't know about numbers or letters or your code. It is purely and only responding to voltage. The moment we say this voltage level means 1 and this other level means 0, that meaning exists only in our heads and in the conventions baked into the circuits we build around it. The machine is meaning blind. Every layer of meaning from here on, bits, bytes, integers, strings, objects. Your program is a story we tell about patterns of switches, not something the switches themselves know or care about. Hold on to that. It's the single most important idea in this entire book, and we'll return to it again and again. Computation is the manipulation of meaningless physical patterns, arranged so that the patterns happen to correspond to something meaningful to us.
Logic gates building meaning out of switches. A single switch can be on or off. Interesting, but not useful by itself. The next step is combining switches into small circuits that implement Boolean logic, the algebra of true-false, which Claude Shannon famously realized in the 1930s could be directly implemented using on-off electrical circuits. These small circuits are called logic gates. Not takes one input, gives the opposite output. On becomes off, off becomes on. And takes two inputs, outputs on only if both inputs are on. Or outputs on if either input is on. NAND, not AND, outputs on unless both inputs are on. XOR outputs on if the inputs differ. Each of these can be built from a handful of transistors wired together in specific patterns. None of this is exotic. You could build an AND gate on a breadboard with a couple of transistors and a battery in an afternoon. Here's the second mind-bending idea. The NAND gate alone is functionally complete. That means you can build a NOT gate, an AND gate, an OR gate, an XOR gate, anything using nothing but NAND gates wired together in different combinations. And since any Boolean logic, and therefore any computation, can be expressed in terms of AND or NOT, it follows that the entire logical complexity of every computer ever built, every operating system, every video game, every neural network, is, at the very bottom, an enormous number of not both switches wired together. Everything from here on is just organization. Complexity isn't added by inventing new physical principles. It's added by arranging the same simple thing, NAND, at staggering scale and with staggering cleverness.
From logic to arithmetic, the ALU. Logic gates let us make decisions if both are on, output on. But computers also do arithmetic. How do we get from not both switches to addition? The answer is the adder circuit. A half adder takes two single bits and produces their sum and a carry bit using a handful of XOR and AND gates. Chain several half adders together, a full adder per bit position, with the carry rippling from one to the next, and you get a circuit that adds two multi-bit binary numbers, exactly the way you add multi-digit decimal numbers by hand, carrying the one except in binary. Collections of these arithmetic circuits, plus circuits for comparison, shifting, and bitwise operations, form the ALU, arithmetic logic unit, the calculator part of every CPU. Now, the third mind-bending idea, and one that genuinely surprises most working programmers. Negative numbers do not exist in hardware. There is no minus switch. Instead, we use a convention called two's complement, where certain bit patterns are agreed to represent negative numbers, chosen very deliberately so that the same addition circuitry that adds positive numbers also correctly handles negatives with zero extra hardware. The consequence, subtraction, is not a separate operation. 7-3 is computed by the hardware as 7 plus minus 3, where is just a particular bit pattern fed into the exact same adder. There is no subtractor circuit hiding in your CPU. Subtraction is an illusion maintained by clever encoding. This is your first real taste of a theme that will recur constantly. Higher-level operations are often just lower-level operations in disguise, made to look different through encoding, not through new mechanism.
Memory giving the machine a past. Logic gates and the ALU can compute, but a circuit made purely of gates has no memory. Its output depends only on its current inputs, this instant. The moment the inputs change, the past is gone. To build anything useful, the machine needs to remember. Memory requires feedback, a circuit whose output is wired back into its own input, creating a loop that can hold a stable state even after the original trigger is gone. The simplest version of this is called a flip-flop, a tiny circuit that can be set to a 1 or 0 and will stay that way, holding its state until explicitly told to change. This is the most basic unit of memory in any computer. Wire a handful of flip-flops together and you get a register. A small, extremely fast storage location the CPU can read and write in a single step, typically holding 32 or 64 bits. Wire millions or billions of them together with an addressing scheme, a wiring system that lets you say, give me the bits stored at location number 4,829,103, and you get RAM, random access memory. Here is the fourth mind-bending idea, and arguably the one that will change how you read code forever. RAM has no concept of integer, string, array, object, true, false, or any data type whatsoever. RAM is just an enormous numbered grid of on-off switches. Every address holds nothing but a bit pattern. When your program stores the number 5, what physically happens is a particular bit pattern 101 gets written into a particular group of switches at a particular address. That's all. The fact that this pattern means 5 rather than the letter representing whatever, or a tiny fragment of an image or part of an instruction, is entirely determined by how the program that reads it back chooses to interpret it. This is why type systems exist, why type confusion, bugs, and security vulnerabilities exist, and why something like C's int casts can reinterpret the same bits as a completely different kind of value. There is no tag on the bits saying what they are. The meaning lives in the program, not in the memory.
The CPU, a very fast, very stupid loop. We now have switches, transistors, logic gates, arithmetic, the ALU, and memory RAM registers. The last piece is the component that ties them together, the CPU, the central processing unit. Strip away every marketing term, cores, cache, pipelines, gigahertz. And at its absolute core, a CPU does one thing over and over, billions of times per second. Fetch, look at a special register called the program counter, which holds the memory address of the next instruction. Go to that address in RAM and read the bit pattern stored there. Decode, figure out what that bit pattern means as an instruction, e.g., add these two registers, load this value from memory, jump to a different address, execute, actually perform that operation, usually involving the ALU and or registers and or memory. Repeat, update the program counter, usually to the next instruction in line, unless the instruction said to jump somewhere else and go back to step one. That's the entire job description of a CPU. Fetch, decode, execute forever until the power goes off. Everything else, caching, pipelining, branch prediction, multiple cores, exists purely to make this loop run faster or more in parallel. None of it changes what the loop fundamentally is. Notice something striking. The CPU has no concept of programs, if statements, loops, or functions. Those are patterns in the instruction stream that we recognize and name to the CPU. A loop is nothing but an instruction that says, jump backward to an earlier address if some condition is true. The CPU has no idea it's looping. It's just following a jump, the same as any other jump. An if statement is an instruction that says, jump over the next few instructions if some condition is false. Again, just a conditional jump. The CPU doesn't know there's a branch in your logic. It only knows it either jumps or doesn't. A function call is save the current address somewhere so you can come back, then jump to a different address. Later, jump back to the saved address. The CPU doesn't know what a function is, it just sees jumps with bookkeeping. Every structure you've ever used to organize your thinking, loops, conditionals, functions, even objects and classes, which we'll get to in a later part, is asterisk a pattern of jumps and memory operations that humans invented because we needed structure to think clearly. The machine never needed it. The machine is and always has been just following a numbered list of tiny instructions, one after another, occasionally jumping to a different line.
The stored program concept, the deepest idea in this part, we've established that RAM holds bit patterns, and that those bit patterns can mean data, numbers, text, or instructions, what the CPU should do next, and that nothing in the bits themselves says which is which. Now ask the question that John von Neumann effectively asked in the 1940s. What if instructions and data live in the very same memory, using the very same representation? This sounds almost too simple to matter, but it is the idea that makes general-purpose computers possible at all. Consider the alternatives. In early computers, programs were physically wired. To change the program, you rewired the machine, plugging cables into different sockets. The program and the machine were inseparable. The stored program concept breaks that link. The program becomes just another pattern of bits in memory, exactly like the data it operates on. Want to run a different program? Don't touch the hardware, just load different bits into memory. This is why you can install software. It sounds obvious now, but it was a genuine conceptual leap. It means the machine you're using is actually defined by whatever bits currently happen to be loaded into it, not by its physical wiring. And here's where it gets genuinely mind-bending, even for experienced programmers. Because instructions are just data, a program can read, generate, and even modify instructions, including its own. This single fact is the seed of compilers, programs whose job is to read one pattern of bits, your source code, and produce another pattern of bits, machine instructions, as output data. Interpreters, programs that read instruction-like data and executed on the fly, rather than running it directly. Operating systems, programs that load other programs into memory and hand control to them. Self-modifying code, JIT compilers, virtual machines, all of these are just exploitations of the fact that code and data were never actually different things. We just usually choose to treat them differently. There is no hard boundary between code and data in the machine. There's only bits in memory and a CPU that's currently been pointed at some of them, treating them as instructions. Everything you do as a programmer, every language, every framework, every layer is built on this one unglamorous fact.
Tracing a tiny program, end to end. Let's make all of this concrete. Suppose, in some future part of this book, you write something that looks like the x equals 5, y equals x plus 3. Well, here is what actually happens, layer by layer underneath that. The compiler decides and y will live at two specific memory addresses, say address 1000 and address 1004. From this point on, the names and y disappear entirely. They were never real, they were labels for humans. An instruction is placed in memory that says, in effect, write the bit pattern 101 binary for 5 to address 1000. Another instruction says, load the bit pattern at address 1000 into a register. Another instruction says, add the bit pattern 11 binary for 3 to that register using the ALU's adder circuit. A final instruction says, write the resulting bit pattern from the register to address 1004. At no point did the machine know about X, Y variables or addition in the way you think about them. It moved specific patterns of on-off switches between specific numbered locations and ran one pattern through an adder circuit built from NAND gates. The meaning, we just computed that Y equals 8 exists only in your mind and in the mind of anyone who later reads those bits with the same convention you used to write them.
Mind-bending takeaways for the reader who already knows how to code. If you've programmed for years, none of the individual facts above were probably new, but the implications, taken together, might reframe how you think about everything else. Every abstraction is a story about voltage. Variables, types, objects, true and false, even numbers, none of these exist physically. They are conventions agreed upon by the people who designed your compiler, your CPU, and your language, layered on top of patterns of switches that don't know any of these stories. Hardware and software are a spectrum, not a divide. Anything a program does, you could in principle wire directly into a circuit. This is literally what an FPGA or an ASIC is. Anything hardware does, you could in principle simulate in software. This is literally what an emulator is. The line between them is drawn for convenience and cost, not because they're different kinds of things. The hardest part of programming was never the syntax. It's that you're permanently operating on two levels at once. The story, your variables, your intentions, this represents a user's bank balance. And the machine, bits, addresses, cycles, none of which know or care about bank balances. Becoming a strong programmer means being able to move fluidly between these levels, to compile your intentions into bit patterns in your head, and to decompile bit pattern level bugs back into the story you meant to tell. Every concept in the rest of this book exists for one reason. Someone decided a particular arrangement of memory and instructions was useful enough, common enough, or important enough to deserve its own name, and to have its messy, bit-level reality hidden behind that name. Arrays, linked lists, loops, functions, objects, even entire programming languages. All of them are named patterns sitting on top of exactly what you just learned. Switches, gates, registers, memory, and a dumb loop that fetches, decodes, and executes. From here on, every time you meet a new concept, a data structure, a control structure, a paradigm, the question worth asking isn't, what's the syntax for this? It's, what pattern of memory and instructions is this concept naming, and what problem made that pattern worth naming?
What's next? Part 2 picks up exactly where this leaves off. How humans went from wiring NAND gates by hand to typing words like if, for, and function, the layered chain of lies, assembly language, compilers, interpreters, that each made the layer below it easier to ignore one step at a time. Understanding why each layer was invented, what specific pain it removed, is what lets you use any programming language as a tool instead of treating it as a sacred text.